Good morning, all of you. So now if you'll notice it, we are doing presently the Faraday's experiments, correct? So this all are what we are studying, everything we used to call as Faraday's experimental. So now if you'll notice it, so the first experiment was, if you'll see, yesterday's what we have studied. So we are having what? Non-conducting cylindrical rod, which made up of paper or something. So now it will be wounded with a wire, insulated copper wire. That is what we used to call as a solenoid. Yes or no, guys? So now the solenoid is connected with the galvanometer. So now we are bringing what? We are bringing either a north pole or south pole of a bar magnet. So if you are doing the relative motion of north or south pole of a magnet inside this solenoid, then we have been found that the galvanometer, we have been seen a momentary deflection. Is it yes or no, guys? Please respond. So momentary deflection, we have been noticed it, and in last class we studied that completely like how it is flowing, what is the direction of the current, and how the galvanometer will deflect everything we have been studied. If north pole will go inside, north pole will come outside, south pole will go inside, south pole will come outside. Yes or no? Yes, the same way as I told you. So now whenever you will keep in front of you the coil, then you remember this side you always will feel the point is A and this side the point is B. Now the same things if it comes to here, if you place this side the magnet, then that is also you have to remember the cases which we have been studied in this side. So this all the 7 cases, if it comes to this side, here also if you follow up, then it will be coming opposite to here. So for example, if you go north pole inside, then as we know that north pole will go inside, what will come, Arvind? Can you tell me? So now if it will go north pole inside, so as we have been seen that if the north pole will go inside, what will come, guys? Then this will be the north pole of the solenoid and this will be the south pole, so that the current will go from
anti-clockwise direction.
Anti-clockwise direction, so that the galvanometer deflecting towards to the right. Is it yes or no? So now the same north pole, if for example, if you have been kept this side at A point, then you remember north pole is inserted this side, then this is north pole, this is south pole. North pole is going inside. If you'll notice it, then this will become the north pole and this will become the south pole of a solenoid. Now here if you'll notice it, the current is moving clockwise direction, so that the galvanometer will deflect towards to the what, guys? Towards to the left. So like this the current will pass. Understand? Opposite to the first case. Okay, Arvind? Bhumika, have you understand this one? So that is what you have to remember. So here what we are getting, here for north pole we are getting right side anti-clockwise. So that if it will comes to the point A, then it will comes to the clockwise and left side will come. So like that, every case you have to imagine, and based upon the situation, you have to make it. Now I will make you one shortcut which we can remember easily, so that all can easily can remember. So hope you all understand. You might be notice it here. See, north pole is going inside. North pole is going inside like this, but deflection is opposite to that. Have you noticed it, guys? North pole is going like this, but the deflection I am talking, deflection is like this direction. Yes or no? Yes, please respond, all of you. Yes. Now here also you see, north pole is going inside like this direction, but deflection is what? Opposite direction. Yes or no? So that is the trick all of you should remember. North pole, whatever the direction it is going inside, then the deflection will be opposite to that. If it is going pushed in, then the deflection is in this direction. And also remember, when we pushed in, understanding, pushed in, then the force is maximum. Force is maximum, means magnetic force is maximum. And when it is pulled out, the magnetic force is minimum. Understand, magnetic force is minimum when we pulled out. That is you have to remember. So when maximum current is induced, when the magnetic force is maximum, means when we push it in, the magnetic force is maximum. When we push it out, pulled out, the magnetic force is minimum. So now I'm saying you, whatever the direction you see, for example, let me take South Pole is going. So now South Pole is going, what you have to remember, guys? You tell me, all of you. So this is the galvanometer. So now South Pole is going inside. So now what is happening? You people tell me. South Pole is going inside. So as we know, this side South Pole, this side North Pole will come. If the South Pole of the magnet is going. So now South Pole I am inserting, push it in, so that force is more. So now you tell me, if the South Pole is going, push it in, so that the deflection is what? Please respond.
Left side, sir. Deflection.
So the deflection is left side, so that the current is moving from where to where? Clockwise direction.
Clockwise direction.
No, this is what it is. You check it, everybody. Yesterday we have been studied the same thing. Yes, Arvind?
Yes, sir.
Yes, all of you check it. If the North Pole is, if North Pole is going inside, North Pole is going. Yes, please respond. Who is that?
Can you please say how to find the direction of current?
Direction of current, that is what it is. Yesterday fully I told you that is the same thing only, correct, Kavya? Now South Pole is going inside, so that the deflection is towards the left. Towards to the left. Deflection will be towards the left, so that the direction of current is, if it is moving, turning like this left side, so that the current is coming in this way. If it is turning towards the right side, current is going in an anti-clockwise. So this is the anti-clockwise direction, and this is the clockwise direction. That is what. Understand, Gavya? So now here, if the South Pole is pushed inside, so that the deflection is what? The momentary deflection is left side, so that it is showing in the clockwise direction. The current is moving from North Pole to South Pole. So now same way, if this side the South Pole is pushed inside, all of you remember. Why I am saying you this? You can easily remember this shortcut to memorize, so that you cannot commit any mistake. Now, for example, this is the solenoid. Now this side I pushed the bar magnet. So which pole it is, guys? South Pole, and this is the what? North Pole. Understand? So then what is happening? Here the South Pole of a solenoid, and here the North Pole of a solenoid. So now magnet is going inside. If it is pushed inside, then the momentary deflection is towards the water. You can say opposite to this. What is that? Towards
Right
the
side.
right side, so that the current is passing anti-clockwise direction. Understand, Pershini, Omega, at least communicate. So anti-clockwise direction. Have you noticed it, guys? Direction of South Pole also same direction. Galvanometer deflection is also same direction. Here also check it. South Pole is going like this direction. Galvanometer is also deflecting like this direction. Yes or no? Yes?
Yes,
so
sir.
that is what I want to say you. So whatever the solenoid, all of you remember, whatever the solenoid and whatever wherever we are placing like either we are moving the solenoid, or else we are moving the soft iron, means this is what is soft iron, not magnetic bar, either North Pole or South Pole, this side or this side, doesn't matter. Wherever you are moving bar magnet, understand, either North Pole or South Pole, inside the solenoid to induce the current. See, two ways we can. Either we can fix the magnet, and we can move the solenoid. Understand? So, or else we can fix the solenoid and we can move the magnet. Both the ways, the same process, the current is induced. One thing, now we are pushing the magnet either A side, this side, or this side. Understand? That is also same direction deflections will take place. If it is bar magnet is fixed in any side and it is coil, the solenoid is moving oscillation, relative motion, to and fro motion, then also the same direction the deflections will take place. Now here the 2 points I want to say. Remember, North Pole whatever either you push it in or pulled out. As I told you, push it time, the magnetic force is maximum, and pulled out, magnetic force is minimum. Okay. So now here, if you'll notice it, when we'll trying to keep the north pole inside. So now remember, if the north pole is going like this direction, then the galvanometer deflection is opposite direction, whatever it is. If north pole is going like this direction, then the galvanometer direction is opposite direction. Understand, everybody? So that is what I'm saying. You can feel the things. If the north pole is going like this direction, you can see galvanometer towards the right side, opposite. Yes or Nora? That is what I can say. That is the shortcut which you can remember to not to commit any mistake. Now, but if it comes to the south pole, if south pole is going like this, then the deflection is also, understanding, galvanometer deflection is also same direction. For example, here south pole is going, then the deflection is also same direction. Or else if the south pole is going like this, then the deflection, galvanometer deflection is also same direction. This is for south poles, any point, either at B point or A point, and this is the north pole at A point or B point. This is what the thing which you have to remember, so that you won't commit any mistake in the directions of galvanometer. So basically at one point only they will give you that point is B point. That B point only 7 cases I have taught you. So now A point also they will give you. You can remember the same thing. Everybody clear? Any doubt? Anybody you can ask me. Please respond. That is what I want. Yes? All of you? Clear, guys? What is this? Nobody is responding. Okay. So now, today's class, anybody is having doubt, you please kindly ask me. No issues. I will again, you want, I will explain. You understand? Krutika?
Yes, sir.
That is okay. So now this is what you have to remember. But this is a very important question. So definitely they will ask you in this or next experiment what we are going to study. In this, definitely they will ask you. So as I told you in last class, we are having 3 factors which will influence this induced current. What is the 3 factors? Anybody can tell me? In this experiment. So 3 factors which will influence that in this experiment. What is the first one? Please respond. What are the 3 factors which will influence the induced current? First one is what? Strength of the magnet. Yes or no?
Yes, sir.
Yes, please. The strength of the magnet. And the next second one is what? You have to speak here. I should say me.
Number of turns in the coil.
The coil.
Turns in the coil. That is the second one. Number of turns in the coil.
Length of the turn. Length.
Relative speed between the coil and the magnet.
Relative speed. So relative speed. Length is a number of turns only length. Correct, Krutika? Relative speed. Understanding speed in the sense of how fast you are oscillating the magnet or how fast you are oscillating the solenoid. Understanding means to and fro motion. Forward and backward, how fast you are doing, that will be deciding the amount of induced current. So relative speed between the coil and the magnet. That is what you have to remember. Between the coil and the magnet. Is it okay, guys? So these are the 3 things. Now, as we know, this is the first experiment done by Faraday's. Understanding. So, and before that, we have been studied one more experiment. What is that? That is a straight conductor is oscillating. A straight conductor is oscillating between the 2 poles. Yes or no? So 2 poles of a horseshoe magnet. So that is what we have been even studied in the last class. Yes or no? So you can take either south pole or north pole here. So then you can take, if you are moving this a straight conductor between the 2 poles of a horseshoe magnet, then you can see this is also in the first experiment. We can use it. The induced current we can notice in deflections in galvanometer, and we can find the direction of conductor, induced current, and as well as magnetic force with the help of what rule, guys? What rule? Last class I told you, correct? So Fleming's right hand thumb rule.
Fleming's right hand.
So right hand thumb rule. So we can use one more rule also. That rule also I have told you. That is only we used to call as Lenz law. Understand? So but Lenz law now is not there. So no need to worry. You'll study in the 12th class. This is also we can use to find the inducer current, direction of inducer current. But basically class 10th we will use Fleming's right hand thumb rule. So yesterday's I have shown you for this experiment how it will come. Yes or no, guys? Please respond. So either the conductor is moving downwards or the conductor is moving upwards. Then the magnetic force is acting like this always. So based upon that, two fingers if we'll adjust, remaining finger will indicate the inducer current. Yes or no? Please respond. That is what we have studied in the last class. The same way, we can find the amount of inducer current or direction of inducer current with the help of Fleming's right hand thumb rule. So Fleming's right hand thumb rule, we are having again three fingers. What is the three fingers? So the middle finger, if you'll see, sorry, the index finger, which will indicate the magnetic field, and if we'll take the thumb, if it is indicating the motion, understand? And if you'll notice it, the middle finger, it is indicating what? Induced
current.
So that is what we used to call as Fleming's right hand thumb rule. So direction of magnetic field. This is the direction of magnetic field. So which finger right is? It is the forefinger. Yes or no? So our index finger. And you can see this one. This is induced current is middle finger. And the thumb. This is what? Motion is equals to what? Thumb. So which is indicating, thumb is indicating what, guys? Direction of motion of the conductor. Yes or no? That is what you have to remember. This is the direction of motion of the conductor, and this is induced current middle finger, and magnetic field forefinger. That is only we used to call as Fleming's right hand thumb rule. Now, today we are going to study the last chapter, last concept of this chapter. That is what? Induced current by current. Understanding current is induced by current only. So last one what we have studied, Faraday's first experiment, current is induced by magnet. Yes or no, guys? This is what we have studied, both this experiment also current is inducing by magnet, and this experiment also current is induced by magnet. Now what we are going to study is very important. In these two experiments, one experiment definitely will be there in your final exam also, you see. Now, this is a little bit easy, but things you have to understand very carefully. Remember, like here. So here, if you notice it, guys, one we are fixing, and another one is relative motion. Yes or no, guys? Please respond. Another one is what? Relative speed. Yes or no? Yes. Please respond. The same way.
Yes, sir.
Yeah, and one is solenoid, another one is a magnet. But now you can take two solenoids. In one the current is passing, another one is no current is passing. So like that also you can take. So that is the experiment 2. So experiment 3 also there. This is not there in textbook, but I am saying you it is also similar to the experiment that the solenoid and the bar magnet. So this Faraday's experiment 2, what will do means the current is induced. Understanding by current. Current is induced by current. So now with the help of magnet we can induce the current, or else with the help of current we can induce current induced by current itself. Now this current induced by current itself we can do in two methods. The two methods I will teach you now. So the first one is, remember, so I will take one coil, one solenoid. Understand, solenoid is not kept any non-conductor also. I connected the galvanometer. So now I will take another solenoid which has been, understanding, connected to the battery. Do you understand, everybody? Which has been connected to the battery. Now when the current is passing in this solenoid, as we know, solenoid, how it will be formed the magnetism? It will be formed similar to the bar magnet. Yes or no, guys? Please respond. It will form the magnetic field similar to the bar magnet, and the magnetic field will keep on moves like this. Will you accept it or not? Solenoid, you all know, no or not? Please respond.
Yes, sir.
Yes? So that is what it is. So now this is what basically the magnetic fields will happen. So now you can notice it here. All of you remember? So this is the coil A and this is the coil B. So whatever the current is passing, we used to call it as a primary coil. All of you remember? Now, another one is called as secondary coil, wherever we are inducing the current. Okay. So now primary coil. So now primary coil current is passing. Secondary coil, nothing is happening. We are connected to the galvanometer. Now, what Faraday has been done means when the current is passing in this solenoid, understand, in this solenoid, now a coil A was moved towards to coil B. Do you understand? When the current is passing in this solenoid, a coil A is moved towards the B, like a to and fro motion. Understand? Like same way how the magnet is moving. So he's used to move the galvanometer, this coil A towards the B and again bringing back, towards the B, again bringing back, like that. He's doing the relative speed, understanding the relative motion, going forward and coming back. Then he noticed it. Understand? Because of the magnetic field created by this, created by in the coil A, will be induced in the current in the coil B also. So that is the experiment he has been shown. So when a galvanometer shows sudden deflection and when coil A was moved away from the coil B, then also the galvanometer is showing the deflections. So it is indicating what? When we are moving the coil A to and fro motion, means bringing towards the coil B or taking away from the coil B, then he has been noticed it that it is showing the deflections in the galvanometer. Do you understand, everybody? It is showing the deflections in the galvanometer. That is what? If it is coming towards to that, remember, if it is coming towards to that, he noticed it, galvanometer is deflecting towards to the right side. Clear, everybody, Bhumika? He has been motion towards to which coil? Coil A is coming towards the coil B. He noticed it, understanding, the galvanometer is deflecting towards to the right side, so that the direction of current is what? Anti-clockwise direction. Do you understanding? So here, because of magnetic field, sir, how the current is induced, sir? Because of magnetic field created by a first solenoid A, understanding, will bring the a change in the magnetic field in the coil B, so that the induced magnetism will act like a magnet. When the current is passing, through a solenoid, it will be behaves like a similar to the bar magnet. Is it yes or no, guys? Please respond. It will be similar to the bar magnet. So that is the reason these magnetic fields will change the magnetic fields around the coil B and they will induce the current. Is it okay? Again, have you understand? So when coil moves towards to the, when coil A moves towards the coil B, then galvanometer shows the deflection is right side, so that we can see the current is induced. Same way, when the coil A moves away from the coil B. Do you understand? It means motion is this direction. Understand, Ra? Please respond, everybody. So when the coil A moves away from that, then you can see in the coil B, okay, the magnetic field is still, but the galvanometer shows deflection towards the what, guys? Towards the left side, so that the current is passing in this way. So the magnetic field created in this is only inducing the current. So this is the second experiment which is done by the Faraday. But here also you notice it, this is not given in our book, but I am saying you. So here also it is working. See, when both the coils are in relative motion, do you understand? When both the coils are in relative motion, you understand, everyone? Means both the coils are coming forward and both the coils are going for each other. Then you can see they are producing an induced current is produced due to the change in what, guys? Due to the change in only one reason. That is what? Magnetic field, or we can say magnetic flux. So why the current is induced in coil B? Means because of when coil A is coming close and going backward, coming forward and going backward, it will cause us to change the magnetic flux flux in coil B. So because of that reason, the current is induced. If the magnetic field is steady, no current is induced. If zero magnetic field, no current is induced. Only when the relative motion, because of relative motion, same way like this experiment also, understand? Why here the current is induced? Because of relative motion, then the change in magnetic field will take place. So because of that reason, it is inducing the current. Understand, Bhumiga? Varsini? Any doubt, anybody, you can ask me. So that is the very important one which you need to remember. The reason behind is, all of you should remember, when North Pole, for example, let me take the first experiment as we know. When the North Pole will come push inside, all of you should see, when the North Pole is pushed inside, understand, then here also North Pole will come. So as we know, North Pole will show repulsion or attraction, guys. North Pole will show repulsion or attraction. The North Pole
Repulsion.
repulsion. Do you understand? So that what is happening? The magnetic flux of this bar magnet will try to push this coil away from it. Is it yes or no? Will try to push this coil away from it. Means the change in magnetic field will take place in the solenoid. So that is why the current is induced. Now, when we are moving this North Pole out of it, then you can see here south solenoid, which pole will come, guys? You might be check it. Solenoid, which pole will come? When the North Pole is going away from it. Check it, second case, everybody. Then it will come South Pole. Yes or no? When the North Pole is going away from it, what will come, Ra? You can check it. Yesterday diagram. Third diagram, everybody check it. Sorry, fourth case. Fourth case, everybody check it. If the North Pole is going away from it. So this is the solenoid. So now you can notice it. Now the North Pole is going away from it. Then what is happening? This side, who will come? Solenoid. This is the South Pole and this will become the North Pole. Yes or no, Ra? Now the current is moving in the deflection is towards the left, and it is going into the clockwise direction. Yes or no, Arvind? Varshini, check it the answer. It is correct or not? If the North Pole is going away from that, then this is the South Pole of the solenoid and this is the North Pole of the solenoid. And if you notice it here, the current is induced. It is deflected towards the left galvanometer and it is clockwise direction. So here what is happening, sir? Why the current is induced? I am saying the reason. This reason is not for class 10th, but I am saying you. Remember, when North Pole is pushed inside, what is happening? Here also North Pole will come so that both will repulse each other. So that the magnetic flux will cause us trying to push the solenoid away from the bar magnet because both the poles will show repulsion. So that is why change in magnetic flux will take place. So it is causes to induce the current. Now, when the North Pole is pulled out from the solenoid, then here the South Pole will come, here the North Pole will come. So by that time, what will happen, guys? It will show attraction or repulsion. It will show attraction or repulsion. It is trying to show the attraction. When the North Pole is going away from the solenoid, then the solenoid here it will South Pole will come and here North Pole will come. So by that time it will show attraction. So it is trying to attract the magnet towards the solenoid. So that is why it is causes loss of magnetic field, means magnetic flux is decreases. So that is also causes induced current. Do you understand, everybody? It is also causes induced current. So because of only change in magnetic flux only, it is possible to induce the current. If magnetic flux, for example, sir, I kept a bar magnet inside the solenoid, then what is the deflection, guys? Anybody? Yesterday we have been studied correct. Suppose I kept a solenoid inside a solenoid, I kept a bar magnet. Then what is happening? No deflection in the galvanometer. Yes or no? So why no deflection, guys? By that time, no change in magnetic flux. Understand, Karthikeyan? No change in magnetic flux, so that our magnetic field, so that no current is induced. That is the reason behind it. Clear, everybody? Akshaya, Tarani, if you have any doubt, you can ask me. This is a very, very important one. That is what I am saying you. The same way here, if it comes to this experiment also, why the current is inducing? Because as we know, when the current is passing across this solenoid, it will be behaves like a bar magnet, because the magnetic field is resembles similar to the what? Similar to the bar magnet. Is it yes or no, guys? So what is happening? When if it is current is if it is trying to come forward, then the deflection is towards the what? The deflection is towards the right side. Where it is moving away from that, motion is away from that, then it is deflection towards the, what is that? Towards the left side. So that is what you have to remember. So now, why it is happening? When it is coming forward, remember the magnetic strength is keep on increases. Magnetic field is keep on increases. So when it is moving away from that, then the strength of the magnetism will be keep on decreases. So both will cause a change in magnetic flux. So that is the reason. Then the relative motion of these coils only will induce the current in coil B with the help of coil A. Is it okay, guys? Clear, everybody? So this is how both the coils are relative motion, then the induced current is produced due to the change in magnetic flux. But this is not given in our book. That is, I am saying you for your purpose. Now, next experiment is here no relative speed. So in first and second experiment, what he found, the relative motion between the coil and the magnet produces induced current. Second experiment, what he have been made, the relative motion between the different coils, which one carries current, produces induced current. Yes or no, guys? Please respond, everybody. So both experiments, what is happening? Because of relative motion only, it is producing induced current. Yes or no, Bhumika? But now Faraday did what he did means in this third experiment. Faraday shows that relative motion is not absolute requirement to induce the current. Puriyama, everyone. So he has been proved that relative motion, understanding, relative motion is not absolute requirement, means it's not a necessary factor. So absolute requirement to induce the current. So that is the reason he has been taken some insulated that is what I told you. So in this experiment, he has been kept both the coils A and B stationary, but coil B was connected to a sensitive galvanometer and coil A was connected to a battery. So that is what. So just he has been put, if you take the textbook page number, how much, guys? Just check it, everybody. I don't know the page number, I forgot. So if you check the page number, that experiment is 13.17, experiment 13.9, activity 13.9, the picture number 13.7 you can see. So there is no relative motion, yes or no? So Faraday said that relative motion is not a absolute requirement to induce the current. So we no need relative motion. Just you can take two coils, understand? So one coil is connected to the sensitive galvanometer and another coil is connected to the battery, yes or no? So for that purpose, he inserted some kind of a rod, a non-conducting rod, or else you can keep a soft iron also. If you keep soft iron, what will happen? Anybody can give the reason? Here I am keeping a non-insulating, a non-conductor, no issues at all. Understand? This is the non-conductor cylindrical rod. Okay. So now instead of that, I can keep this soft iron bar also. Then what will happen, guys? Soft iron bar, if I'll keep, then we can increase the
electromagnetic.
We can increase the galvanometer deflection. Do you understand, Karthikeyan? If you place the soft iron bar, then it will be turned into electromagnet. I am not asking that, but we can increase the amount of magnetism so that the galvanometer deflections will increase. Yes or no? Yes, please respond, everybody. That is what you have to remember. But textbook they are saying non-conductor only because we are studying only induced current. So now you have to take two coils. So one coil is connected to what, guys? See the textbook and tell me. One coil is connected to the battery. Yes or no? Yes. So this is what it is. So now one coil current is passing. Now another coil is connected to what? Another coil is connected to the sensitive galvanometer. Understanding? Sensitive galvanometer. So this is what? A galvanometer. So this is the experiment given in our textbook. Is it yes or no, guys? Please respond. So one is connected to the galvanometer and another one is connected to the voltage. Now, when the current is passing in this, understand? So here the current is induced. Now, how it is induced, why it is induced, everything clearly we'll study. So please everybody log in back. This is the most important one out of all the concepts. Now you can see, guys, here both kept stationary but a near distance. Remember, this is the coil A, where the current is passing. That is what we used to call as primary coil. That is only called as coil A. And where the current is passing, where the current is induced, that is what coil B. That is what